Welcome to Lab 4. In this lab, we will go through sequence recognizers, we will talk about clock dividers, and debrief on debouncers, and we'll finish it up with the tasks expected for Lab 4. A sequence recognizer is a sequential circuit which can identify a sequence and then react to the correct and incorrect sequence of inputs provided by the user or the environment. Now, there are multiple examples of sequence recognizers in the world. So for example, classifiers, you have control systems, even artificial intelligence are part of sequence recognizers. And the one most relevant to us is the password recognizer. As talked about in the lecture slides, in the lecture videos in UTS Online, there is a design flow to create a sequence recognizer, and they follow as such. So initially you would develop a sequence recognizer state diagram. So if you look at the image on the bottom left, that is a state diagram. You should formulate a state table based on that state diagram. So as you can see in the image on the right, that table, this is your state table. And then from there you should assign state to codes, whether it be gray code or counting order, and then you would derive the Boolean expression for each for the flip-flops required for the sequence recognizer. And then finally, you're going to draw the schematics in Xilinx and implement it on the hardware. So in our case, once we've designed the sequence recognizer, we'll draw it in Xilinx and implement it on our MXK boards. In applications, sequence recognizers have applications around the world. So for example, this is example number 1. A robot is working at high speeds in a robotic cell. When the human enters the work cell, the robot slows down to a safe working speed to prevent or mitigate injury to workers around the robot. So if you look at this example, you can see there are two states. The first state is when there are no humans working around the robot, and the second state is when there are humans around the robot. And obviously, with the two separate states, the output that is changed, or the stored information that is changed, is the working speed of the robot. So in state 1, when there are no humans in the working cell, the robot will work at higher speeds. And then in state B, so when a human enters the work cell, there will be some form of sensors to detect that, and that triggers the state to state B from state A, which is when there is a human in the work cell. The robot will then slow down to a safe working speed. And conversely, when the human leaves the robotic cell, in your state diagram, it would go back from state B to state A, indicating that there are no humans around and the robot can resume working at high speeds. Another example of this could be on trains. So as you can see in the image down here, that is an image of the high-speed rail in Japan. So this sequence of events, so for example, when the train is turning on its tracks, this sequence of events can be applied to sequence recognizers as well. So again, you have state A and state B. So state A is when the train's going forwards without turning, and state B is when the train's turning a curve. So as you can see, direction of curve. As you can see, the air springs will tilt the cars when the direction of when the train starts bending around the corner. And again, that could be analogous to our two states. So state A is when the train is going straight, then the air springs will not activate, and then state B is when the train turns around the corner. For our labs, we'll go through the two input example. So in MXK, so in assignment 1, you are required to design and create a password recognizer to recognize the last 4 digits of your student number, a binary coded password. So in this lab, we'll go through an example of that with a 2 input example. So To start off with, you need to draw your state diagrams for the sequence recognizer, as you can see as such. So you have two states, state A and state B. When a 1 is pressed, state A transitions to state B, and when a 0 is pressed after that, the output is successful. So the sequence required to create a successful output is a 1 and a 0. And obviously, incorrect inputs will then take you back to state A. As you can see, if you press a 0 initially, output would be 0, and it returns to state A. And in state B, when an incorrect input of 1 is pressed, the output is still 0, but you transition back to state A, which is your initial state. From the state diagram, you should then derive a state table. So as you can see, you have your present state, your next state, and your output, and your input being X. So if you look at the current state A and current state B, you have your transition to the next state and your output. Now, after you have your state table, you should assign state codes to them. So in our example, we have two states, A and B. We can code that with A is equals to 0, B is equals to 1. So if we encode that, so take note that A, where the present state is 0, that is A, and where the present state is B, 1, that is B. So as you can see, at state 0, if the input is 0, you remain in state 0. But if at state 0, you input an input of 1, you transition to state 1, and so forth. Your outputs will be the indicator of whether the password entered or the sequence entered is correct. So there is only one instance of that happening, which is when you've pressed both sequences correctly. So a 1 and a 0. So when you press a 1, you go from state 0 to state 1. And then at state 1, when you press a 0, you successfully unlock, or you successfully recognize the sequence. Now, from this state table with assigned codes, you are now required to derive the Boolean expression for the flip-flop. So in our case, we have one flip-flop representing the current state. You can expand that as much as you want. So for example, if a system is more complicated and has more than say 8 states, you can the assignment of the state codes can be done with 3 bits. So from state 0 to state 7, that's 8 separate states. You can encode that with 3 bits, meaning you have 3 flip-flops to store the current state, or the current to store the memory of each bit at the current state. But in our example, we only have 2 states, which only requires 1 flip-flop to keep track of our present state. Therefore, you need to acquire the Boolean expression for this flip-flop, D0 as we call it, and then from there you should then draw it out in the schematics in Xilinx and create the symbol and implement it with your hardware. Now let's talk about clock dividers. So clock dividers, as the name suggests, divides the clock input into lower clock speeds. Using the binary system, so what we use with 1s and 0s, each division will half the speed of the clock. Now, the hint that we suggest is think of what the ripple counter does to the clock input. And in this image you see at the bottom, that is that CB16RE should be in your template project, your Xilinx template project file in the top level. And what it does is it divides the clock input into divided by 2 to the power of 16. So as you can see, you have Q15.0, which means it's a data bus of bit 15 to bit 0, meaning that you have 16 different data lines, data wires available in this one data bus. But with clock dividers, do you think about what the ripple counters do to the clock inputs at each stage, and try to use that to achieve the last bit of assignment 1 part B. Now we won't go in too much into clock dividers because it is a part of your assessment, so this will require you to spend some time understanding how it works and how the ripple counter works, and see how you can implement that forwards. Now, let's talk about debouncers. So when a switch is pressed, the contacts of the switch will have to physically move from one position to another. As the contact settles in a new position, they mechanically bounce, causing the electrical circuit to open and close several times. So if you look at the image at the bottom, you have a simple pull-up circuit. So when the switch is closed, your voltage would turn to 0. So initially it's high, and then when you push the switch, it becomes a low. So that's an active low circuit. As you can see in these waveforms, when the switch is pressed, you have these noise of your switch. So as you can see, as we mentioned, they mechanically bounce, meaning that instead of the one instance that we require down at the bottom right over here, it actually activates 4 instances of a low logic. Therefore, we need to find a way to filter out these outliers and only push in the correct input to our circuit, into our circuitry. So in an electronic circuit, the stuff that happens on the circuit board itself is much quicker than what we can perceive. So as you can see over here, that's 50 microseconds, which is much quicker than what we can see or perceive, meaning that even though we might not see this result, in the digital circuitry, that is a very crucial part. So for example, if you were to have a sequence that accepts whether it's up or down, so when you press up, the values increase, and when you press down, the values decrease. If without a debouncer, when you press up, the value could increase 4 times instead of once, as you want it to. That's why we need a debouncer to filter out this noise and be able to input a clean signal into your digital circuitry. Yep, so example, in order to ensure the signal outputted to the circuitry is a clean signal, debouncer is used. It passes the input signal through multiple flip-flops to filter the noise. So do note that for assignment 1 part B, the debouncer is already in the template Xilinx project. It should be available. If you go to your files, you should be able to see it, and then you should be in your symbols. If you write debouncer, you should be able to use that in your top level. Now, this is the example debouncer in your template project file. As you can see, the input is then fed through multiple flip-flops, and it's only until all 4 of them push back the same result that the clean signal is then outputted into your digital circuitry. Now, for lab 4, the tasks you are required to attempt or finish is to extend this 2-input sequence recognizer, that in this example, to fit your assignment. So remember to review the lecture videos for other examples of sequence recognizers, and also remember to review the assignment requirements to fully understand what's required from you for this assignment. And by this time, you should be finalizing assignment 1 part B for marking. Uh, Further references include the FAQ for Assignment 1 Part B, available in your Assignments tab, Assignments page, and also uh, lecture videos and previous lab videos to help you complete Assignment 1 Part B.